The introduction to trigonometry, with our first focus being on the concept of building and measuring angles. And if you look up here, what we said in class was that to build an angle, what we do is we connect two rays. And if you go back to your geometry days, a ray is something that it's a part of a line. It's part of the line where you choose one endpoint. So you kind of break up the line, you give it a starting point, and then you let it run off in a direction, never stopping. That's what the concept of a concept of a ray is. Now, to build an angle, what we do is we put the endpoints of two different rays together. That location where the endpoints meet is called the vertex, and then we let the rays go off to the sunset, so to speak. And what's in between? How far apart, for lack of a better term, will be a little bit more precise down the road, but an angle represents just how far apart these two rays are from each other. Now, from a variable standpoint, when we do angles, we're going to start using Greek letters rather than using the letter X or Y, something of that nature like we usually do in everything we've seen so far. You'll see angles are usually going to be used or represented. The variables associated with them are going to be Greek letters. And the most common one you'll see is this last one, the Greek letter theta. Now, some other basics to work our way through. Again, a lot of this is summary, but it's going to be important information to carry with us as we walk through this whole unit. Complementary angles. Two angles are complementary when they sum up to 90 degrees. Supplementary angles, you probably remember, two supplementary angles sum up to 180 degrees. An angle is called acute if it's, and I'm going to do this just so we get used to it. I just put angle theta between 0 and 90, and notice what I just did. I made a degrees mark on each one of these. Degrees is going to be the first unit that we use in this section. Obtuse angles between 90 degrees and 180 degrees. So that's the basics of some facts with angles. When we put an angle in what we call standard position, this will kind of be the base way of building an angle. It's going to follow this process. We're going to build an XY grid. Our initial ray, just like you saw here, our ray, the first one that we build, is always going to start with a vertex at 0 and run along the positive x-axis. And then we'll go ahead and place the second, what we call the terminal side or the terminal ray, wherever we feel like it. So standard position, vertex always at the origin, initial side always running along the positive x-axis, and then we choose where we want to connect, so to speak, that second ray. I kind of said in class, you could kind of use this as an example. You could kind of treat my thumb as the initial side, and then whatever I happen to do with my index finger, I can only stretch so far obviously, would be the terminal side. And that little angle sitting in kind of the web of my thumb here, between my thumb and index finger, that's kind of the measure of the angle. Obviously, I don't have enough flexibility in my finger, thank God, that I can rotate all over the place, but that's the concept. Initial side, terminal side, angle lives in between them. Now, an important point. When we build an angle that is considered to have a positive measure is going to go in a counterclockwise direction. This angle that you see here, kind of see they put a little arrow move here, like we move along a little arc. Start from your initial side, go to your terminal side. That's a positive angle. A negative angle is going to be built by rotating clockwise. So it's maybe a little bit counterintuitive, but just make sure you realize that. Positive, counterclockwise, negative, clockwise. When you go all the way around, let's pretend our initial side, and I decided to make my terminal side land right on top as well. Well, that could be a 0 degree angle, but more properly, we would think, hey, I just did a full revolution. I got right back to where I wound up. That's a complete circular revolution, complete circular motion. One revolution's worth is considered 360 degrees. And you're probably familiar with that. You did a 360, you turned around, you got right back to where you started with. So just remember, 360 degrees constitutes a perfect trip, a perfect revolution from a degrees standpoint. Now, what I asked you to do after that in class, and for those of you who missed, we're going to repeat the same thing. This little example asks you to draw 3 positive angles and put them in standard position, do them wherever you wanted. Well, standard positions would, for all of these, just kind of be this little red line. I'll go ahead and do that. Whoops, excuse me. And then I gave you some certain angle sizes I wanted you to build. I said a 45-degree angle. Sorry, this is a little bit too small. Let me just fix my handwriting real quick. I asked you to build a 45-degree angle, and you went right like this. And my little 45-degree angle lived right in that little nook. I asked you to build a 170-degree angle, and most of you realize, hey, I just go a little bit short of half a revolution. And you finished with your terminal side somewhere like that, and here comes your angle. And then I asked you to do a 285-degree angle, and you realized, oh, well, hey, 180. You also realize, hopefully, as you move through each of these little poles, so to speak, you're going 90 degrees at a time. And so 285 degrees would be approximately around here. And there's your angle that would build 285 degrees. A couple other things we talked about, I'm going to use down here as just our little example. These little poles, so to speak, represent the beginning and ending of what we're going to call quadrants. Each of them represents what? 1/4 of a revolution. So as you move from quadrant to quadrant, you're traveling 90 degrees at a time. But I wanted you to make note that this would be called quadrant 1 in the upper right, quadrant 2, upper left, quadrant 3, lower left, quadrant 4, lower right. These will be important concepts that we'll use down the road. That's a good idea for us to get familiar with them next. Last piece, rather than arbitrarily build a couple negative angles, I asked you to build something that was negative 315 degrees. Now, as you do that, well, remember, negative 315, you better be going clockwise. So, hey, when I get to here, negative 90, negative 180, I just traveled 90 more degrees, negative 270, and then I need to do what? Go another negative 45 degrees. And it turns out that a negative 315 degree angle, starting here on the initial side and rotating around, winds up in the same place as a 45, a positive 45 degree angle. And this leads us to a very important concept. These two angles are called coterminal. They're built in different ways, but they share the same terminal side. And hopefully you've caught on how far apart are these separated from each other? The equivalent of a full circle revolution. The distance between negative 315 degrees and 45 degrees is 360 degrees, a complete revolution. And so if we go to the next page, that leads to a very, very important definition, which we're going to use over and over again. We're going to learn that angles of different measures can wind up in the same place. Therefore, they will be called coterminals. And coterminal angles are always separated by positive or minus 360 degrees. And by the way, I could do multiple revolutions. I could do a 720, so to speak, from an angle and wind up in the same place. So any integer multiple of 360 degrees, whether that's positive or negative, leads us to coterminal angles. So some quick examples. Find two angles that are one positive, one negative, coterminal with 270. Well, all I got to do is do 270 plus 360. I'll get a 630 degree angle. That's another positive one. By the way, if I added another 360, I would have gotten 990. That's legit as being coterminal as well. A negative angle, what could I do? Well, I better go in the opposite direction since I'm already in positive angle territory. If I subtract 360, I get negative 90. So hopefully no surprises here. And the second example, 115 degrees. Find another positive one. 115 plus 360, 475 degrees. 115 minus 360 is negative 245 degrees. So 115, 475, negative 245. Three very, very different angles, all sharing the same terminal side. So be comfortable with the concept of coterminal. It's pretty intuitive, at least what it means. Co, same, terminal, terminal point. Same terminal point, same terminal side. Right, now the second part of our lesson focused on triangles. And if you go back to what we did A little while ago in our circles unit, remember that little bow tie diagram that we used? There's similar triangles lying all over the place. There's symmetry lying all over the place. There's quadrants lying all over the place. You're going to see that document again, that illustration, that picture, many times as we move forward. And one of the key concepts in there is there were many triangles that we built. Each piece of the bow tie, each quarter of the bow tie, produced a similar triangle. So some properties of triangles. The three angles in a triangle, when you sum them up, you always get 180 degrees. In order to have a true triangle, in other words, for your shape to be an absolutely positively guaranteed triangle, the combined length of any two sides must be greater than the length of the third side. And it has to be true all across the board. It can't be just one combination that you choose that does this. It has to happen for everything. So pick two sides, add their lengths together. That value has to be bigger than the length of the remaining side that you did not choose. And a couple other pieces. In a triangle, the larger angles are opposite the larger sides. Smaller sides are opposite smaller sides. If you want to go one step further, the largest side of a triangle is opposite the largest angle. The smallest side of a triangle is opposite the smallest angle. And our last piece, similar triangles. Again, we're going to see them over and over again. In similar triangles, corresponding angles are equivalent or equal to each other, and corresponding sides are proportional. So in other words, similar triangles, it could be that every side in one triangle is half as big as the corresponding side in the other triangle. It could be, hey, every side is 3 times as big as the corresponding triangle in the other one, corresponding side in the other triangle. Bottom line, corresponding angles always equal, corresponding sides proportional. And that helps us in a number of ways. For instance, and you'll see this as you work through some practice problems, similar triangles, we can compare shadow lengths, build our own little triangles to estimate things that we could not measure directly, such as the height of the Washington Monument. The Washington Monument casts a shadow, I cast a shadow, and our angle to the sun is essentially the same because the sun is 93 million miles away from us, and so the angles are going to be the same. So it turns out that the shadow that the Washington Monument makes and the shadow that I make build some similar triangles. And so, with this structure, my 6-foot height generates a 7-foot shadow. The Washington Monument's unknown height generates a shadow that I can measure. I can pace off this and measure 647.5 feet. And similar triangles tell me that what? The ratios of our respective heights should be equal to the ratio of our respective shadows. So I can say 6 is to h as 7 is to 647.5. And if I do some simple cross multiplication, 6 times 647.5 divided by 7 gives me an h of 555 feet, which if we go to good old Wikipedia or whatever, turns out to be a very good Washington Monument 555 or 556 feet in measure. We have a very nice representation here. So building models like this, things that we can measure, leaving ourselves with something that we can't measure, similar triangles gives us the ability to figure out that unknown. Now in this lesson, there's one more important piece to work our way through, and that is some special right triangles. A lot of what we're going to do as we begin through this unit is going to use right triangles. They're very simple and manageable for us to work with. What are some of the nice things about the right triangles? Well, in the first place, a right triangle is going to have one 90-degree angle. We know that. But the other lovely thing about it is the hypotenuse is going to live, and we can measure, and the Pythagorean theorem holds in a right triangle. The length of the hypotenuse, c squared, is equal to nothing more than, let me just go ahead and mark my triangle here. There's AB, the two sides, and there's the hypotenuse. A squared plus b squared equals c squared, the Pythagorean theorem. And we're going to work with two very special right triangles. that have some very nice characteristics going to help us out greatly as we start measuring angles and developing trigonometric ratios pretty soon. And those are the 45-45-90 triangle and the good old 30-60-90 triangle. And what we're going to find out, there are very predictable relationships amongst the lengths of the sides in these triangles and the hypotenuse. If you have one of these two triangles and you know just any of the sides or the hypotenuse, you can figure out the lengths of everything in these triangles. And so here's what we're going to do. We're going to do that. We're going to build those ratios and relationships. In a 45-45-90 triangle, what I can consider is having myself a square and then running a diagonal through. A diagonal serves as a bisector, so each one of these little 90 degrees measures in the square. Well, this one still stays as 90 degrees because I didn't touch it, but the bisector here cuts this 90-degree angle in half, and that one as well, turning this into a good old 45-45-90 triangle. Now, for simple purposes, I just set these sides of my square at 1, and that tells me that what? That h squared equals 1 squared plus 1 squared by the Pythagorean theorem. H squared equals 2, and h equals the square root of 2. And so what that tells me, and we'll do one more example. Let's just pretend these were bigger. Let's pretend that the sides were 3. What would I have then in that triangle? H squared equals 3 squared plus 3 squared. H squared equals 18. H equals the square root of 18, which happens to equal square root of 9 times square root of 2, 3 times the square root of 2. So what do I notice in a 45-45-90 triangle? It's this little summary that you're going to see down here. If you know the lengths of the sides, all you need to do is multiply that by the square root of 2, and you'll know how long the hypotenuse is. Pretty simple with our original example. And when I made the sides equal to 3, what did I notice the hypotenuse came out to? 3 times the square root of 2. Conversely, if you know the length of the hypotenuse, to get the lengths of those two equal sides, all you need to do is take the hypotenuse length and divide by the square root of 2. Possibly as you're doing this, just depending on what type of triangle you have. Here, these were very, very clean to work with. Just remember, you might have to do some denominator rationalizing, some one of those old Algebra 1 tricks and things that we've done. We did earlier in the year as well in our review at the beginning of the year. In a 30-60-90 triangle, we have a concept that we can work with an equilateral triangle as our foundational structure. Equilateral triangles are such that what? All three sides are the same. It also means that all three angles are the same. Angles in a triangle add up to 180 degrees. If you have a triangle with three angles that are the same, each angle must be 180 divided by 3 or 60 degrees. So this angle right here, by the way, I know is 60. I build a perpendicular bisector. What's the beauty of a perpendicular bisector? It's twofold. Number one, it cuts this angle in half and makes this little angle up top here a 30-degree angle. It's perpendicular, so by nature, it builds a 90-degree. I have a 30-60-90 triangle. The last remaining nice piece that I get out of this type of triangle with this perpendicular bisector particularly is what? It cuts this length of the base, which was 1 in my equilateral triangle, it cuts it in half. And so this length of this side down here is 1/2. What is the good thing now? Well, I know two pieces of my triangle. I just need to get this side that lives opposite the 30-degree angle. I'm going to call it B, just to give it some type of value. And what I know in this case is 1/2 squared plus B squared equals 1 squared. 1/4 plus B squared equals 1. B squared equals 3/4. B equals the square root of 3 over 4, square root of the whole thing. Remember that the square root of a fraction can be represented as the square root of the denominator the square root of the numerator divided by square root of the denominator. So this can become the square root of 3 over the square root of 4 or the square root of 3 over 2. Again, I could work with different numbers. I could make this equilateral triangle 4 times as big, 4 times as small, whatever. The same relationships would hold. And take note. The angle, 30-degree angle, produces a side that is 1/2 the length of the hypotenuse. If I know the length of the side opposite the 30-degree, I can multiply that by the square root of 3, excuse me. I can multiply by the square root of 3 to get the other ratio. So what do I have? Smallest, 1/2. Hypotenuse, 1/2 times 2. Side oppo, 60 degrees, 1/2 times the square root of 3. So smallest is oppo, 30 degrees. Sorry for my handwriting here, but just understand the pieces here. And so what does that mean? Again, as long as I know one of the sides, I can build what I need. So there's a lot here covered. It's pretty basic stuff, but please spend some time with this. Get familiar with it. Understand these relationships because they're going to be so important as we start solving these types of triangles.